Tithonus, a mythical Trojan prince, was so handsome that he caught the eye of Eos, the goddess of dawn. Bewitched by Tithonus, Eos requested to Zeus that he grant Tithonus immortality so that she may have him forever. However, Zeus took her request in the most literal sense. Tithonus never did die, but he did age. Over time, his beauty disappeared, and with it so did Eos. His strength dissipated until all he could do was babble endlessly, wishing for the sweet release of death that never came.
Since at least the time of the ancient Greeks, humans have dreamt about immortality. The idea of never dying, of staying forever youthful, has captured our minds and money. Whole industries, scientific and cosmetic, are dedicated to keeping humans feeling and looking young. We do as much as we can to extend life as long as possible, seeking any way to avoid our inevitable mortality. Recent research suggests that we may soon be able to take on such a task successfully, within limits. And here is where we will begin our journey into the prospects of immortality. This series will explore the intriguing science, reality, and ethics of immortality, and much more. It's going to be a fun, fascinating ride, so I encourage you to keep on watching and subscribe. Alright, for clarification, immortality most always refers to biological immortality, in which the effects of aging are negligible, and thus chronological age is irrelevant. From molecular analysis to uploading our consciousness into robots, we may soon live in a world where average lifespans are counted in centuries, and aging and the diseases that come along with it are no longer a threat to our existence. In order to theorize how we could solve the puzzle of mortality, we must first understand the science of how we die, and ultimately why we die. The process of aging is called senescence. This process is typically described as the deterioration of the physiological functions vital to survival and fertility over time. As opposed to diseases of aging like cancer, the characteristics of aging affect all members of a species. Recent investigations have supported the idea that factors like genetics and diet can modulate or affect the lifespan determined by senescence. Some of the things scientists have been looking into include the effects of telomeres, which are thought to play a role in the aging process. So what are telomeres? Well, telomeres are extra base pairs attached to the tips of chromosomes. These non-coding repeats of DNA don't code for a gene, so we can afford to lose them. Their primary purpose is to protect genetic data from mutations or other errors. A telomere is to a chromosome as an aglet is to a shoelace. During the process of DNA replication, a small piece of RNA called a primer attaches to a DNA strand and initiates the copying process. Because DNA can only be copied in one direction and the primer does not attach to the very end of the DNA, a portion of the strand does not get copied over to the new strand. Thus, with each cell division, less and less of the end section of the original DNA gets synthesized. Estimates suggest that humans lose between 50 and 250 base pairs per cell division. It's after about 50 divisions the telomeres shorten to a critical point called the Hayflick limit that tells the cell to stop dividing in order to prevent damage to coding DNA. As a result, most often, the cell dies in a cell suicide called apoptosis. Not only do shortened telomeres lead to individual cell suicide, but they are also associated with organism-level aging, cancer, and death. Babies are observed to have telomeres of about 8,000 base pairs, while adults have 3,000 and the elderly only average 1,500 base pairs. The fewer the base pairs, the more susceptible the cells are to aging and incorrect functioning. There is, however, an enzyme called telomerase that extends the lengths of telomeres by adding base pairs to their ends. In young cells, telomerase protects the telomeres from too much wear and tear. However, as cells divide repeatedly, telomerase levels run scarce, and subsequently, the telomeres grow shorter and the cells age. Telomerase remains active in germline cells such as sperm and eggs. In a sense, these gametic cells are immortal, as they don't age with time. The reason for this is so that the baby will actually be born a baby. This sounds redundant, but take Dolly the sheep for example. Dolly was the first successfully cloned large animal. However, the cells she was created from had already aged a few years. Thus, when she was born, her cells were already aged that many years. This caused many problems for Dolly, including an almost immediate onset of issues like premature arthritis. So, if telomerase can maintain telomere length, making cells immortal, then why don't we just inject our cells with more telomerase so that we can avoid aging altogether? Problem solved! Actually, not really. The problem lies in the relationship between telomerase in somatic cells and cancer. Cancer cells activate telomerase so that they can become immortal. Cancer is uncontrollable cell growth. Because the telomeres don't shorten, the cells never stop dividing and a tumor grows. In theory, if we can stop the production of telomerase in cancer cells, we may be able to stop the cancer as the cells will be forced into death. Research has tested this in a laboratory setting with human breast and prostate cancer cells, and just as proposed, the blocking of telomerase caused the tumor to die. However, telomerase blockage comes with several risks, including impaired fertility, lowered blood production and clotting, and a weakened immune system. If we could utilize telomerase in such a way that the risk of cancer is small, if anything, scientists would have the ability to mass-produce cells. With no limit on cell availability, scientists could further research on pharmaceutical drugs and gene therapies, as well as have a greater supply for transplants and other specialized cell treatments. Clear research suggests that those with shorter telomeres live shorter lives. For example, those over 60 with telomeres of sub-average length are 3 times more likely to die from heart disease and 8 times more likely to die from infectious disease. One study showed that people with longer telomeres lived, on average, 5 years more than those with telomeres shorter than their own. Nonetheless, correlation does not automatically equal causation. Although several studies show a strong relationship suggesting shortening telomeres contribute to senescence, it is possible that telomeres are merely a sign of aging. In fact, also thought to contribute to senescence is damage to organic molecules and organelle functioning as a result of things like glycation and oxidative stress. So, as with most everything in science, more research is needed. End screen! Hey YouTube, I haven't seen you in a while. So I'm planning on revamping this channel. I'm not exactly sure what kind of videos I want to post yet. I'm definitely gonna go through with this series. My science music videos are definitely my most popular videos, and I do have a lot of sciencey songs that I've written that I haven't posted, so if you guys want to see those, let me know. So I started this channel when I was freshman, 8th grade-ish, something like that, and I'm going into my senior year of high school now, and you can expect in the coming months a lot of varied type of videos as I try to figure out like what I like to do, what I like to post, what gets the most views, what people respond to the most. My videos are probably going to range from this exploratory kind of stuff to lessons, to practice problems, to science music videos, to school-related academic stuff in general, like my experiences in different classes. I don't know, I think those would be fun to make, but I guess we'll see. So yeah, if you made it to the end of this video, please give it a like and subscribe and comment your thoughts on this topic and what other areas you'd like to explore with me. Something. Alright, bye.